Alright, what's up guys? Welcome back to another video. So this is chapter 2 now, which is titled Conditional Probability and Independence. So first thing we're going to look at is section 2.1, which is the definition of conditional probability. And the easiest way to explain it would be, what is the probability of an event given that a previous event happened? And that's what that looks like. This is what it looks like. So we have, let's say we have two events, A and B, and we're trying to solve the probability of B given A. That's what the straight line means, the separation line. The probability of event B given event A. And the formula, or like the expression like written out, is this. It's the probability of B intersect A over the probability of A. And this is moving a lot. Alright. So this is the formula for finding the probability of an event B given that event A has already happened. We take the intersection of events B and A, and we divide that by the probability of event A. And also, we can only do this if the probability of event A is greater than 0. If the probability of A is 0, then obviously this whole thing would be 0, or what is it? What do they like to say? Undefined. So the probability of A has to be greater than 0. And I mean, this is also like another way of being able to find, either one of these probabilities. Like, let's say we're given already the probability of B given A, and it asks us to solve for the intersection. Well, we would pull up this exact same expression, plug in what we know, and then solve for that. So yeah, if we were asked to find the probability of B intersect A, well, that would just be the probability of B given A. And in order to get the probability of A to this side of the equal sign, we would have to multiply both sides by the probability of A. So yeah, this is just like another form that we can write this in. So yeah, I mean, we can be given any two of these other probabilities and asked to solve for the third one. So some important relationships regarding this would be, so there's also like a complement rule, right? Where it's 1 minus the event is equal to the complement, or 1 minus the complement is equal to the event. Well, the same thing applies here. Like, the probability of B complement given A is equal to 1 minus the probability of B given A. So yeah, if we're asked to find the probability of the complement of B given A, well, the same sort of rule applies, where you would subtract the probability of the event from 1, right? And it works both ways. If we were given the probability of B given A, and we were asked to find the complement of B given A, then it would be 1 minus the complement equals the probability of this thing. So there is a complement rule as well. There's also the very long, what if we're given the union of two events? And What do I mean by that? Well, remember the Venn diagram expression, the really, really long one where you add, then you subtract, and then you add at the end? Well, that same rule applies here. If we were given 3 events, now we have A, B, and C, and we have the probability of B union C given A. Well, this can be written as the probability of B given A plus the probability of C given A minus the probability of B intersect C given A. Right? And again, what this does is it prevents us from double counting by subtracting out an intersection. And I'm sure, like if we had a 4th event, like event D, then, this would only extend. You would add plus D given A minus, and then all those intersections, and then you would add in the final 3rd intersection at the end. So, yeah. So these same like rules and relationships, they cross over from like chapter 1, whenever we're given like simple events A and B, but it also applies if we're given, or if we're asked to find the probabilities of events B given A or C given A. So all of that, like I said, comes over from chapter 1. All right, so let's do like a quick example showcasing this stuff. All right, so all right, so we'll use our 6-sided die example again. So if you'll remember, the sample space of a 6-sided die is 1 through 6. 1, 2, 3. Oh, that's ugly. It's 1 through 6 because those are the 6 possible faces that a 6-sided die can land on. All right. Now, let's have 4 separate events. We have event A, and we'll say A is that an even number is tossed. So that would be the faces 2, 4, and 6. And we have B, let's say that a number is less than or equal to 3. So that's 1, 2, and 3. We have event C, which is we either toss a 1 or a 2. So that's just 1 and 2. And then we have event D, which is a number is tossed that does not start with the letters T or F. So that's 1 and 6. All right, our sample space, and we have 4 different events. An even number, a number less than or equal to 3, a 1 or a 2 is tossed, and a number is tossed that does not start with the letters T or F. So, all right, so let's say we're asked to find the probability of B given A. So, remember that this is equal to the probability of B intersect A over the probability of A. So what's B intersect A? Those are the things that are in both B and A. All right, so we look at B, 1, 2, and 3. We have A, 2, 4, and 6. A 2. The 2 is the only thing that lands in both A and B. So we can put that up here as like that. And then we put that over the entirety of A, which is 2, 4, and 6. All right? 2, 4, and 6. Now, we have 1 point in the intersection of B and A, and we have 3 points in event A. So we can rewrite that as 1/3 because we're just counting the sample points that are in both. And that's our answer. So the probability of B given A is equal to 1/3. All right, what about the probability of B given C? So remember, the numerator, just like this one, would be the intersection of B. In this case, it'd be the intersection of B and C. So, okay, what is in both B and C? 1 and 2, all right? 1 and 2. Now, what is in C, right? Because C would go in the denominator, 1 and 2, all right? So 1 and 2. So how many sample points are up here? 2. How many sample points are down here? 2. 2 over 2, that is just 1. And, right, so, you know, if we tossed, this is like saying like, okay, let's say we tossed an even number. I'll use this as an example. So P given A. So let's say we tossed an even number, right? So that's A. So we tossed a die and we landed on, you know, either one of these. Then what's the probability that only given these faces to land on the next throw, that it would land in a sample point that is in B? Well, there's only one possible chance, there's only one possible sample point it can land on that is in B, which is 2. Similarly, right here, what if we tossed, you know, either a 1 or a 2, because that's what's in C? Then what's the chance that, you know, just choosing from these two sample points, the next throw that we toss also lands in one of these sample points from B? Well, it's a 100% probability because 1 and 2 are in both C and in B, if that made sense. And actually, hopefully what I just said is better explained in next example where we use, you know, some urns and like, oh, you'll see, I guess. Okay, so yeah, that was an example using a die. All right. I guess we didn't need D, but it's just there. All right, we'll do another quick example. Okay. So let's say that the probability of A is 1/6. The probability of B is 5/12, and the probability of A given B plus the probability of B given A is 7/10. What is the probability of A intersect B? All right. So, all right. So we're given these probabilities up here, and we're asked to solve the probability of A intersect B. Now, this basically, if you know, from what I just erased, remember that the probability of, you know, A intersect B is, or A given B is the probability of, I'll just write it out. So the probability of A given B is equal to the probability of A intersect B over the probability of B. And similarly, all right, over here, the probability of B given A is equal to the probability of B intersect A over the probability of A. So whichever event is on the right side of this given line is what's in the denominator. See? So B is on the right side here, B goes on the bottom. A is on the right side here, A is on the bottom. All right. So now that we have these expressions written out, we can solve for, or we can try to solve for this right here, A intersect B. So, all right, how do we do that? Well, we have we can start like replacing some terms here. For example, and actually, I might have skipped over on writing something down. No, I didn't. Okay, no, I did not. Okay. So yeah, we'll start replacing terms. I guess really the only one we can replace here would be this probability of B in this expression. So we have that the probability of A given B is equal to the probability of A intersect B over 5 over 12. And this can be rewritten as 12 over 5 times the probability of A intersect B, right? All I did was take the reciprocal of 5 over 12, which is 12 over 5. That way, instead of dividing it like how we're doing here, we can multiply these together. So this is the same thing as this. And we can do the same thing over here, where we have this is equal to the probability of B intersect A over 1 over 6. But we can rewrite this as 6 times the probability of B intersect A. All right. So we're up to here, right? Now we can use this third thing that they gave us and plug these in, and what we get is this. So we have that the probability of A given B plus the probability of B given A is equal to 7/10. Now, replacing these terms here, this one and this one, we get 12 over 5 times the probability of A intersect B plus 6 times the probability of B intersect A is equal to 7/10. Now, remember that if A intersect B and B intersect A are the same thing, they're just flipped. But it's still the same expression. And so with that information, what we can do is we can combine these two P probability expressions into one and have just the one be multiplied by both 12 over 5 and 6. And what I mean by that is, instead of having it written out long like this, we can simplify it a little. 12 over 5 plus 6 times the probability of A intersect B is equal to 7/10. All right? And 12 over 5 plus 6 is 45. It's 42 over 5. 42 over 5. Is it still in frame? Yes. 42 over 5 times the probability of A intersect B is equal to 7/10. All right. Now what we can do is multiply both sides by 5 over 42 in order to get rid of this 42 over 5 here, because we're trying to solve for the probability of A intersect B. So 5 over 42 on this side and 5 over 42 on this side. Remember, we're multiplying. Multiply by the reciprocal to get rid of it. And then over here, same thing. Multiply by 5 over 42. And I'm going to erase a little bit. So that way we're given. Now this is going to, we're going to get rid of this, so that way we only have the probability of A intersect B on this side. So that the probability of A intersect B is equal to 7 over 10 times 5 over 42, which is 1 over 12. Boom. And that's our answer. We were trying to solve for this probability. We got 1 over 12. All right. Also, guys, Mexico beat South Korea yesterday. Hell yes. Mexico played kind of like Dookie, but a win is a win. All right. All right, here's another important relationship that we're going to immediately use with an example. So remember that, well, I'll just go ahead and write it. In terms of conditional probability, if we were asked to find the total probability of an event, it would look something like this. The probability of B, the entirety of B, is equal to the probability of B given A times the probability of A, and all right, plus the probability of B given A complement times the probability of A complement. All right. Like I said, we're going to immediately use this in an example here in a second, but what this is saying basically is if this first event happens, then the second event will happen. But we also have to consider the fact where that first event doesn't happen and the second event still happens. And that's why we add the probabilities of A complement. So like I said, we're gonna use this right now. Okay, this is a longer example, but it'll illustrate this a lot better. Okay, so let's say we're given 2 urns, right? And urn 1 has 2 white balls and 2 black balls. Urn 2 has 3 white balls and 2 black balls. An urn is chosen at random. Find the probability that the chosen ball is white. Okay? So, let's start at the top. The first event that happens is that we choose an urn. An urn. Alright. So, so there's 2 urns to choose from. We have urn 1 and urn 2. So urn 1 is chosen. Choosing urn 1 points us in this direction. So what's the probability that we choose urn 1? Well, that's just 1/2. Because there's only 2. Alright? But let's say we chose urn 2. This is where a complement comes in, right? Because now we have, since we're choosing from 2 urns, then there's 2 different directions that we can take this in. So what's the probability that we choose urn 2? Well, it's also 1/2, right? And here's where that a complement comes in, because instead of choosing urn 1, we chose urn 2. So again, choosing whichever urn we choose, it leads us in different directions. But let's keep going in the urn 1 direction. Okay, so we chose an urn at random, and it happened to be urn 1. So remember that it said urn 1 had 2 white and 2 black balls. So ball from urn 1. Okay? So we choose a ball at random. Well, let's say that the ball we chose is a white ball. So now this is the probability of B given A, because we're choosing a white ball. It's asking us for the probability of us picking up a white ball. So, alright, so now what's the probability that we chose a white ball? That's also 1/2. Urn 1 has 2 white and 2 black. So the probability that we chose a white ball is 1/2. It's 2/4, 1/2. Alright, so that is equal to 1/2. Now, what's the probability that we chose urn 1 but picked up a black ball? It goes this way. That's also 1/2. And we would denote that by the probability of B complement given A. Right? So the A comes from the fact that we chose urn 1. The B comes from the fact that we chose a white ball, and the B complement comes from the fact that we chose a black ball. Given A because we chose urn 1. And you would include that in both scenarios where we pick up a ball. So again, this is also 1/2. Okay. Now, let's fill in this other direction over here. So instead of choosing urn 1, we chose urn 2, which is a complement. All right. So we pick up a ball from urn 2. Ball from urn 2. All right. What's the probability that we picked up a white ball out of urn 2, which is B given a complement? So the probability of B given a complement. So maybe I should write like a little legend up here. So A means we chose earn 1. A complement means we chose earn 2. B means we chose a white ball. And B complement means we chose a black ball. Alright. So, I wrote this thing right here, and again, this is just like a little legend that lets us know where each variable came from. So, okay, we chose a white ball out of earn 2. And in earn 2, there are 3 white and 2 black. So that means it gives us a 3/5 probability of choosing a white ball from earn 2. 3/5. But what if we chose a black ball? Then it gives us a 2/5 probability. And this is the probability of B complement given A complement, which is 2/5, right? Because we chose a black ball from earn 2, black ball B complement from earn 2 A complement, which is 2/5. Okay, now what we're interested in is the probability of us picking up a white ball at all. So now we have to look at 2 separate scenarios. The one where we picked earn 1 and picked up a white ball, and the one where we picked earn 2 and picked up a white ball. All right? So let's go in this direction first. We chose earn 1 and we picked up a white ball. Then, since we already have probability of A and we have the probability of B given A, then the only thing left to solve for is the probability of B complement A. Right? Because this is us saying, what is the probability that we chose earn 1 and we picked up a white ball? Or we picked up a white ball and we chose earn 1. And remember, from rewriting our first expression that we looked at, this is the probability of B given A times the probability of A. All right, B given A is 1/2 times 1/2, that is 1/4. All right, so this is only half of the equation, because now we have to look at, well, what if we chose earn 2 and we picked up a white ball? And that's this scenario right here where we got 3/5. So the probability that we chose earn 2 and picked up a white ball is B intersect A complement, because we're interested in the scenarios where we pick up a white ball. It doesn't matter which earn it comes from, but the question is asking us the probability of us choosing a white ball at the end. Okay, so here's another probability that we need to solve for. So this is equal to the probability of B given A complement times the probability of A complement, similar to over here. So B given A complement is 3/5 times the probability of A complement is 1/2, and that is equal to, what I write? 3/10. All right. So now we found the 2 intersect probabilities. And again, I repeat, we're interested in the total probability of us choosing a white ball. So now all we have to do is just add these 2 together. Because, again, this one comes from us choosing a white ball from earn 1. This one comes from us choosing a white ball from earn 2. So what's the total probability that we picked up a white ball at all? It's 1/4 plus 3/10, which is 11/20. So So 1/4 plus 3/10 is 11/20. Well, I only really had to circle this bit right here. So that is the total probability that we chose a white ball, and again we had the scenario where we had 2 urns to choose from, so we had to consider every single possibility. Urn 1 white ball, urn 1 black ball, urn 2 white ball, urn 2 black ball. And we didn't end up using these over here, but it's still good to see where each probability came from and how much that probability is. But at the end, we only needed the scenarios where we chose a white ball from either urn, and then we find that intersection probability, and then we add it together to give us the total probability of us choosing a white ball. And that's it for this section.